So this literally is the second last lecture, but for the last lecture coming Friday, I'm not going to talk, but you guys going to give a final presentation. So we have about 60 students, and then 3 of them a group. Therefore, we would roughly have 20 groups. We only have 3 hours, which is 180 minutes, and we have
and the break.
So about it'll be about 5 minutes each. Yeah, 5 minutes. 5 minutes. I started more, but yeah, let's do 5 minutes per group. So what I would like you guys to prepare is that slides, 5-minute slides. So I would reckon maximum 5 slides, include the title. Because sometimes I believe you have a lot of things to say. Past period told me that some people even have 20 slides on a stage. But obviously we don't have 60 students last year. But so what I'm gonna do is that I need to come up with a schedule. I think what I by the end of next Thursday, I will give you the schedule. But I think what you need is start to prepare these 4 slides, 5 minutes slides. And if you've got 3 person in the group, I really encourage you, everyone have the opportunity to talk a bit about what's good. Maybe just 1 or 2 sentences. As you show you are involved in the project. And that's it. I'm really expect some of the projects, but definitely very interesting. So I think what you really need is consider me as a sort of potential sponsor or anything that try to sort of say, okay, this is a project. What I'm going to do, why is it interesting, and how you can finish out the project. What do I expect from the project, and that's it. You don't need to have any definitive answer. You can just pose a question, say this is the direction we're going to go, not necessarily to give a result. Any question about the final presentation? Okay, so today we're gonna focus on data analytics because we only have about 3 hours for that. So we're going to focus on association rule mining, but also talking about some of other techniques. We're not going to go to the detail about other techniques, but just quickly review the major techniques that you might encounter in the future for your career or any data analytics problem you want to address. So I first talk about data mining in general, and then have some specific data mining problem. For people who are in machine learning programming, definitely know what is classification, clustering, and that question already. So what I do is gonna quickly review some of the very basic techniques, so that for the people not in the machine learning program, able to appreciate those techniques and know what would be the basic technique algorithms that you can use. So we're going to talk about classification, clustering, associated rule mining, and the anomaly detection. So why mine data? So in the beginning of the course, I briefly talk about the importance of data mining nowadays. It's simply because we have a lot of data. We got data from the web, from the internet, from e-commerce, and also because we have the computer will be able to save, record all the data, right, from the user's data, from the purchase, transaction, bank, credit card information, transactions. And as we see that perhaps individual transactions may not necessarily to be meaningful. May not necessarily to be meaningful. But if you aggregate them together, they become very, very useful. Think about what we started last week. We talked about collaborative filtering. Essentially, is that if you have rich few movies, provide weighting, it doesn't really interesting. It's not really interesting. But if you aggregate them together, you can do many clever stuff, right? We can talk about personalization, collaborative filtering. That was one of the important examples. And also for the commercial reasons, is that if you have the data, become very valuable, and then put it in your very competitive position, much better position compared to your competitors who perhaps doesn't competitors they don't hold the data. Therefore, the question is, once you got this data, how can you make use of it to extract knowledge, pattern out of it? So the data mining. Sometimes you also find the term like knowledge discovery in database, KDD, is in fact is something about data mining, right? In the research community, there's a conference called KDD, ACM, American ACM, computing machinery, ACM, KDD, knowledge discovery and database conference is the top data mining conference. And so the definition of data mining, in fact, is non-trivial extraction. So it's not, if it's trivial, it's easy, then it's not really data mining. But it's definitely say you need to find something hidden there, some pattern hidden there. And when you do exploration, do some proper analysis, is that sometimes, of course, you need to get human involved. But what data mining will help you is some algorithm computer could help a bit to come up with semi-automatic. In most of cases, semi-automatic. In some cases, some tasks you can do that perform the task automatic. But in most of cases, semi-automatic method. So the knowledge can be in a different form. So it could be the rules. It could be the frequently occurring patterns. It could be clusters. So the data mining become a field is the last 20 years also, and in the industry become more and more important, but also as a science and scientific discipline is also become a subfield in computer science. So what is not data mining is that has to be non-trivial extraction. So look at the phone number in the phone directory is not. If you query a keywords search engine, you use search engine, it's not really a data mining, it's information retrieval. So if you want to find what would be the popular surname or popular name in certain region, that is data mining, because that's some pattern that you want to get. Sometimes involve the aggregation of the data. And the clustering. So if you group similar documents together, it is a data mining. So the origin of data mining is you probably heard machine learning, pattern recognition, statistical database. So these are the fields, and then the data mining, in fact, is coming from those fields. It's combined of those research efforts. Does anyone know the difference between machine learning and the pattern recognition? Are they the same or different? So it's just my personal opinion. I think that pattern recognition machine learning is essentially the same, but it's just different research community. They have pattern recognition, who in fact they talk about this, try to recognize pattern, try to let the machine do some clever stuff, but they are more from the physics perspective. In the beginning, I think about 30 or even longer than that, is in the physics they scan some of these raw materials, and they're using some imaging sciences, and they find that because of imaging, advanced imaging science, people can get some pictures of it. Therefore, they want to find some patterns. That's why the pattern recognition stuff. Where in machine learning, this they roots from the neuroscience, but essentially they talk about the same thing. The traditional techniques where pattern recognition machine learning talking about is being able to perform some of data mining tasks, because now the data become large scale and high dimension, and they also belong to different sources, different type of data. So it's also distributed. It's become very difficult and challenging. So what machine learning is interested in is scalability, if you like, and to deal with those problems. And also they have some new type of problem emerged. So where traditional pattern recognition, traditional machine learning, or even traditional statistics research, database research, we could not really find suitable solution yet. So that's the area that data mining is really so it's more on data. In terms of tasks, there are two types of tasks. One is descriptive tasks. They are more the tasks in fact are focused on find patterns. Whereas predictive is that you, based on the previous data, you try to predict some new patterns. So that's the difference. And here's a summary of some of these major tasks. If you're talking about classification, which is predictive, you try to predict the label. I would say examples. Clustering, which is you try to describe. Descriptive is try to describe the existing data. Regression is again predictive. You try to predict some variable that is unknown at the moment. So because we covered in machine learning already, what we will focus on, we're going to focus on unique data mining task that is unique to data mining, where machine learning people or statistics people perhaps they don't really pay attention to. So we are going to focus on today is focus on associative mining and outlier detection, where user interest mining, collect filtering stuff, click through data analysis we already mentioned previously in this class. And so this is a summary of the focus in data mining. They focus on stability, dimensionality, reduced dimension, looking at these different data, different type of data. How can we sort of deal with? How quality of that? Should we clean up the data? The distribution, right? The ownership. Some people do the data mining, is want to aggregate information from different parties, but some different parties don't want to review the data sometimes, but they want to ask you to do analysis. Sometimes it's really impossible task, but that is the situation you might have. And also privacy preservation. You want to preserve your privacy while trying to do analysis. For example, one of the questions people studied was about if you want to use a profile, you want to gather the user profile, try to construct personalized model, make a recommender system works. But sometimes you say, okay, user provide data, but they don't want to review what are the movies you watched in the past. can you preserve the user privacy while still do collaborative filtering? So these are the tasks that data mining is interesting. And also last one is the streaming. Streaming. In many cases, data continuously come over. So can you do the some of data mining task over there? So before I start this associative mining, let's quickly go through some classic, if you like, some classic task. First, we're going to talk about classification. So classification is that, let's say you have a collection of records. So in machine learning, you call it training data. So the record, you can consider each record as an object, where each object contains a set of attributes or features to describe that object. And let's say one of the attributes, in fact, is a class that represents, let's say, the type of the object it is. And the classification task, or the classifier, in fact, is a model of class attributes, where each model is, in fact, as a function of the value of other attributes. Meaning that if you know the attributes, if you know the other attributes, and you want to predict the label of the class attribute, that basically is a classification. So the goal is that, let's say you have training data and train a model, coming with a model, and then you have the previous unseen records or object, but you have observed some of the features, and you want to using it to assign and assign the class as accurate as possible. Basically, that's the classification. So I'm going to give you an example later. So usually what happens is that you split the data into training and test. You use the training data to get a model, and then apply this model in the test set, and to see or predict whether it's correct or not. So it's quite similar to collaborative filtering that we talk about, where you have the user item matrix and you build a new model, whatever is collaborative, user-based, item-based, or SVD, and then there's a new test user comes in, and you try to make prediction and then test whether it's correct or not. Here's an example. Suppose, let's say, you're a tennis player, you want to play tennis every day, but not inside, but outside. The weather obviously is would influence whether you were able to play, especially in UK, right? So what you need to do is that you have the previous weather data as also has the, given this condition, whether you'll be able to play tennis outside in the court. And you have this, let's say, 14, you record 14 days, the weather, and that would be able to allow you to play tennis or not. So this can construct your training data. And as I said, that in the classification task is that once you have this data, then now you have, based on this, suppose today the weather is, blah blah blah, you observe, and then you try to predict whether you're able to play tennis today or not. So this is in fact what I try to say here. You're using this as a training data, and then you classify, build your model. Now, suppose today's weather can be denoted as X prime. So today, outlook is sunny and temperature cool, humidity is high, and the wind is strong. Can I play tennis or not? And then putting it to the model, and the model basically tell you, okay, perhaps today is yes, perhaps today is no. But that's basically its classification. Any question? A little bit of best now. remember when we talk about a language model, we talk about probabilistic information retrieval. We talk about what is prior distribution, what is conditional distribution, and what is Bayes rule. So here, let's review some of the concept here. Let's say you have got a random event, random variable, which is x, and where the prior probability is probability of x, without seeing any information. The conditional probability is that you have one event, you have another event. You observe one event, you want to estimate the probability of the other one. So that's conditional probability. Joint probability is to look at probability of the two events jointly happening together. Whereas the joint probability can be fractionalized into conditional probability and product. And this one is something to do with independence. If there's two events, they are independent, then you will be able to fractionalize the joint probability into prior probability, or the right variable is called marginal probability. So that's the basic math about probability. And then the Bayes rule is in fact that suppose you have x, which is the current today's weather, which can be represented with some of the attributes. You observe today's weather. You want to estimate the probability today you are able to play tennis or not. So you basically pick up the probability which is highest. As the probability of play is higher than 0.5, perhaps you're going to pick up. Or the classifier going to say today it's very likely you'll be able to play. And you need to calculate this probability. So this probability, in fact, can be used in Bayes' rule because you can't directly calculate that in most of cases. But if you apply Bayes' rule, therefore you need to have, this is called likelihood, and this is called prime. So you have a probability of how likely, without seeing any data, how likely you'll be able to play the tennis or not. So let's say if you're in UK, the probability of playing tennis without seeing any information, perhaps this will be lower than in France. So it's a prior probability. It's nothing today's information is observed. And then you apply the likelihood, where it says today, suppose today I play tennis, right? And this is a probability that the feature would, the event, the weather attribute would occurs when you play. And why they call it likelihood is because you're gonna look at, instead of x, look at the thing. You put a different model there, put a different fact there to see how likely this would fit to the data, right? Fit to the data that you observed. So this is called a likelihood. So let's go to the specific calculation. So what I said is in fact called MAP classification rule, or in other words called maximum a posteriori probability. Why it's called maximum a posteriori probability is that if you look at this, so this is a posteriori. You basically say I have different classes. So the previous example, today is play tennis or not. You have two classes. I would choose a class which has highest probability among the rest, right? So if you have a two, today yes or no, and then the probability of play yes, given the current weather, would be higher than the probability of not play tennis, given the current weather. So that's that equation means. So you're going to pick up the class label that has highest probability. But as I said, this posterior probability can't directly calculate. What I can do is use the Bayes rule to transform it into two parts, and this posterior proportional to the likelihood function and the prime, where this bit and this bit can be calculated using training data. Any question? So the first equation on the top is the posterior probability is proportional to the likelihood function given the label and how given the label what is the probability of the values today, and then this is the prime probability of the label. The difficulty is the first one, the likelihood function, which is joint probability, because we have features. Sometimes you might have hundreds of features or thousands of features. It's very difficult to calculate the joint probability. The example we just have a few features, that's fine. But in most of the cases, we might have hundreds, thousands. What you can do is that you can have come up with a simple assumption. Say, okay, this is joint probability, and we consider that, say, assume that if you know the label, if the label is given, and these features, these attributes, they are independent. If you have that assumption, you make program much easier because they are independent conditionally, and they can be factorized into, as I said, the marginal probabilities. Here is that you can factorize into that given the label, I want to observe that particular attribute, probability of that particular attribute. And that can be independently calculated. Therefore, you can factorize, multiply them together, you will get joint probability. So, based on that, the classification rule is that you have this individual calculation of class and prime. You're going to pick up the one, pick up the class which has maximized, that the maximize this equation. So here, given the example we have, is that this individual probability likelihood function can be estimated from the previous data, and equally for the prime as well. So so given the example here, you can work it out. For example, let's say the prime probability of play or not. How can you come in with that calculation? You forget about this, say, because of the prime probability. You look at this yes, and no, and see how frequent yes is, how frequent no is. That is your prime probability. And then let's say the likelihood. Let's say if I yes, and what is probability of sunny? Outlook is sunny. So you can also work it out that for all the yeses, right, which is the play tennis, and the portion of it, whether it's sunny, and then you will be able to work out that. By doing this, you can in fact is to, in the learning phase, when you have that table, the historic data, you could calculate, say, the relationship, if you like, the label with individual attribute. Like if you play, and out of 9 instances, out of 9 days, 2 of them in fact are sunny. Therefore, the probability that if probability given that today is play, and whether the outlook is sunny is 2 divided by 9. Then obviously you can do this for the rest. Therefore, you would have the calculation about this 1, 2, 3, 4, 4 attributes. And then of course you have this prior probability, which basically here that out of 14 days, there's 9 days it's yes, and 5 days is no. Any question? So quite straightforward, right? Are you able to calculate that? Sure. Once you have that table, and let's say today is a new instant. You've got this today's attributes ready, and then you will be able to look at the table. You'll be able to calculate if today is yes. Okay, I'm going to calculate likelihood of yes. If it's yes, and the probability, what the likelihood if today is yes, what the likelihood of no is if today we're not able to play tennis. And then you apply the equation that we just had, the MAP equation. Calculate yes, and calculate the posterior of yes, the posterior of no. So given the calculation, is today the classifier would output yes or output no? No? No. Yes. So the no one knows. Yeah. Good. Any question or any objection? The computer is wrong.
Always.
Well, yes, a certain probability, yes, but so it's my possible. So, but that's the beauty of probability is to able to handle the uncertainty. Okay, this is a classification. This is very basic classification, but the key is that using this naive classifier, you will be able to write a code and perform classification task. A classification task, in fact, how many programs can be formulated as a classification program. Let's look at example. Direct marketing. Suppose that you want to reduce cost of mailing by targeting a set of consumers like to buy new cell phone product. So if you have your customer email address, and you wanna, instead of sending, you have a new product coming on, instead of sending the emails to everybody, what you can do is that you can target to set of consumers. So how can you target? How can you select those consumers and to send an email to them? And the approach is that you can say, I can do classification. I can formulate that as a classification problem. What I can do is that, so instead of doing this, can I ask you what would be the solution? If I give this task, let's say I'm a sensor. I have this. What's the new one?
S1.
Sorry?
S1.
X1. Okay, so I got a population, which is the current customers who use Apple phone, let's say. We want to reduce costs sending the mails, just send a target one. What would be the solution? Can we construct a classifier? give you 30 seconds.
So we need information about them plus history about whether they bought a similar product before, or something you could assume would give an indication about whether they're likely to buy a new product. It would be difficult to test that.
Sorry?
It would be difficult to test.
This will be difficult to test. That's true. So the problem, the solution would be, say, you definitely need to have the attributes. Definitely need to have attributes about your customers, right? And then you might have. You also definitely need to have labels about the products. Perhaps you can use a similar product as you said. And then you look at that their attributes. They buy or not historically. They buy or not, and then try to do prediction. So look at these, perhaps these additional data like demographic, lifestyle, etc., interaction, so on. All the rest of the data you can always comment. But in this case, it's true that it's very difficult to evaluate. But you could start with really small group of customers to try immediately and see whether it's good, and then before you in a large audience. Similar case, you can use it to fraud detection, right? So if you have a credit card transaction, previous transaction data, and you want to figure out now for the future transaction whether that transaction is fraud or not. What you can do again here, you can construct a classifier for that by using the previous transaction as a trading data, because for the previous transaction, some of it it's a fraud, it's not fraud. Therefore, you can using naive classifier build exactly the classification model that we just talked about, and to make the prediction. In practice, Google use it for news classification. For example, they have these topics. Yeah, and then I have no idea why they put in one Chinese category there, but perhaps it's something I'm interested in. They put this category, and then for this news, this is also a typical example of streaming data. You have the new data coming every day, and you want to categorize this into this, let's say, top stories, different categories. You can build this classifier, and then a big prediction, and perhaps you can also receive the user feedback to refine your classification for the accuracy. So one question though here is that here we have multiple classes, not only binary yes or no. So how can we build this multiple class classifier in this particular case? So it's not really yes or no task, right? We've got this 1, 2, 3, 4, 9 categories. What is the solution? So the easiest one would be, say, for each of the category, we're gonna have yes or no, right? Whether it belongs to the word category, yes or no. I'm gonna calculate the probability. Therefore, I'm gonna pick up one which is highest. That's might be a simple solution for that. But in classification, this is a problem. It's called multi-class classification problem as well, and they have some approach for that. The single one is using for each class you consider it as a binary classification problem. Okay, before I go for regression, another question is, remember what we talked about yesterday, recommender system, collaborative filtering. So is it possible to formulate recommendation problem as a classification problem? If the answer is yes, how can we do that?
You train the classifier to predict if it's relevant or not, and then you can use the estimated probabilities by the classifier to plan the document or the items.
Yeah. So you can, well, in the binary case, that you're gonna predict whether you're gonna like for a given item. You're gonna predict whether you're gonna like it or not, and this has become your label, right? And then the rest of the ratings for the previous items, you can consider as attributes. Therefore, for the attributes, you're gonna predict whether you're gonna like it or not. That's the basic one. You can extend it to say have a multiple labels in the sense that you have rating from 5 to 1. You can also do the trick as well. But in that case, that regression might make sense because you have label 1 to 5. Pick up.
That'd be the dead thing.
So that leads us to regression problem. So in some of cases, its classification is not suitable because the label you want to predict is not really a discrete. It's not really a yes or no question, but rather say it's continuous valued variable. So when I say continuous variable, think about the stock market, the price of the stock, the return of the stock. So it's not yes or no question, it's rather it's a value. You need to predict that particular value. So it's a starting statistics in the neural network field and also in economics, econometrics as well. An example, say, I want to predict the sales amount. I want to predict the revenue. I want to predict the revenue velocities. I want to predict stock market indexes. And so the common proposal is linear regression. But given the limited time, I don't think I'm going to talk about linear regression. But it's fairly easy to, if you don't know and want to know it, it's fairly easy. If you Google linear regression, clustering. So we talk about classification, regression. They are predictive. So that means you want to predict something you don't know. But clustering clustering analysis is something different in the sense that you're gonna try to understand your current data, try to understand your existing data. You want to extract some pattern out of that. So cluster analysis is one of these things you want to do when you try to explore the data. So basically, define a group of objects that in such a way that within a group the objects will be very similar. In different group, the object will be different. So here is an example. Say you have the data in the three-dimensional space, and we say, okay, naturally there's three groups. The groups here, from the attributes perspective, they're quite similar. So that sort of things called cluster analysis. You want to inter-class distance, minimize, whereas inter-class distance are maximized. That in fact is what you want to do. So it's have many applications. For example, again, the search engine here is that you want to cluster the result into different cluster results. So here is slightly also something to do with classification as well, because you need to have these the labels of the cluster, and you want to in bioinformatics, you want to group the genes, proteins that have a similar functionality. And you want to group stock with a similar price fluctuation. So these are the practical applications. But it's very difficult. Sometimes it's very subjective. So let's say here, how many clusters do we have?
6.
6. Well, some people might say 2. Some people might say 6. Some people might say 4. So it's very subjective. It's really difficult. If we don't agree, people don't agree, how the computer will be able to generate that. So there's a 2 clustering techniques, or 2 type of clustering. One is called hierarchical, and another partitional. So the partitional is that we just show that you have data and you try to classify into different subsets. Where hierarchical is really based on this, we're able to handle that. It depends on how detailed you want. In different details, therefore you will have different clusters. So partitional, as I said, is that you want to partition into different groups. Where hierarchical is that you would say, okay, I'm just here, I just split it into 2 clusters. If it's 2 clusters, this is one cluster, this is another one. I think this is a little bit too big, so I wanna, if I go deep into this, I can cluster it into 2 clusters, and then go deep into this and go to it again. So it's like you have this hierarchical things going on. Then it basically generate a tree-like diagram. So we're going to talk about this, the King-Means cluster, this partitional cluster. It's very simple, yet it's very popular based on. It's very computationally a bit expensive. As this is a very simple one, you can just 2 lines of code, well, 2 lines of solo code. The input is basically k, the number of clusters that you want to create. And then you randomly have the initial centroid. So basically randomly assign the center of the clusters, of the k clusters. Say that you form this k cluster by assign all the points to the closest centroid. So basically for each of the points, you calculate distance towards this initial centroid. And for each of the sample points, you pick up the one which has the smallest distance and consider it as your centroid, belong to the same cluster. Therefore, you create k clusters. Once you have this k cluster, obviously the center, the original centroid may not necessarily be the new centroid. Therefore, you can recompute the centroid of this cluster. You can take the, take a mean. You can take the mode, whatever you can take, consider as a centroid. And then repeating this procedure again until it converges. So the initial centroid is included randomly, and the interesting thing is that it really depends on initialization. If the initial centroid is different, and the result might be different. So the centroid you usually choose is you take the closest with similarity. You can use whatever you want to choose. For example, unit distance, cosine similarity, correlation, and those is stuff that we know. And so in most of the cases, you can converge. And so here, example. Suppose that this is the data we got. In the first stage, we have this cluster focused on this, basically on the top. And once this k-mean runs, different iteration, you will have different centroid. At the end, you can see that the result converts that into these three centroid. So it's where the clustering, as I said, sometimes quite subjective. How can you properly measure whether it's good or not? So one way you can measure is to measure the sum of the squared error. So you look at this distance for each cluster. You look at this for each sample in a cluster. You look at the distance to the sample, and then in this case, you can calculate the squared distance, and then you calculate this across all the cluster. You get these so-called SSE, and the smaller, obviously, the better. And you can use it to sort of measure how good the algorithm is. However, it really depends on the number of clusters, right? If you have a larger K, will the SSE would decrease or increase? Well, here, as I said already, so reduce the SSE is to decrease the K. So why? If you have a higher K, higher number of clusters, you would reduce the sum of the squared error.
There are as many clusters as points, you can reduce it to 0, so you just put the cluster at each point.
Yeah. So the extreme case that you have the same cluster as the number of samples. Therefore, the errors of the distance is 0. So in the end, the squared error is 0, right? So this is the smallest value you get. But in general, you can use it to measure whether that is a good one or not. So in this case, you know that this is by visually examined. Here is that seems quite optimal, quite good. And here that you in fact have 4 clusters, but it in fact doesn't really represent the data. Although in this case you might have a smaller square error. Another way is to calculate the similarity matrix with respect to the cluster labels. So you basically calculate the similarity of any 2 pairs, and then you have this similarity matrix, and you sort it based on the labels. For example, you got label 1, label 2, label 3. You can actually visualize to see these are the label 3, let's say cluster 3. Therefore, have very high similarity. Whereas for the labels for the samples in different cluster, you would have really small similarity. So that by visually looking at this, the table, the similarity matrix, you would be able to visually examine whether it's a good fit. So that's another way. So in this example, it's really not really obvious there's a 4 cluster, but you can look at this the similarity matrix. It actually shows it's a bit blurred. It's a bit unclear with the distance within class or distance intra-class across the clusters. So applications. and marketing, right? You can cluster, partition the population. You could also study social networks by detect community, establish the community, and information retrieval, and crime analysis as well. Any questions? Okay, I think we can have take a break, and coming back into that.
Maybe part of it, that's it. It's nice to get to lecture.
Yeah, that's true, actually.